Understanding e to the ix equals cosine x plus I sine x in the context of infinite sums. Now, to fully understand how this equation comes together, you'll need to understand a few mathematical concepts like what is an infinite sum and how do we represent this equation in that form. To start out, let's take a look at the infinite sum that approaches e to the x. It's defined as a summation from n equals 0 to infinity of x to the n over n factorial. To visualize the way this approaches e to the x as n tends to infinity, we can graph the series at different values of n, starting with 0. If you're familiar with polynomials, these graphs should all make sense when you simplify the terms. Because we're raising x to the nth power, the order of the polynomial increases with n. So we get the corresponding curves, constant, line, parabola, cubic, and so on. But as n approaches infinity, the sum of these starts to look like the graph of e to the x, and as expected, if we plug in 1 for x here, we get e. You may have noticed that I'm avoiding the paradox of evaluating this an infinite number of times by saying it approaches, but it's important to understand that theoretically and notationally, the series is equal to the function. This process can be applied to many other functions too. Here's the expansion for sine x. This one is more complicated, and I won't even get into why this sum approaches sine x, but I will point out one of the many interesting patterns that emerges here. For every term that we add to the sum, x is raised to a certain power, and this is defined in the summation where we see x to the power of 2n plus 1. Interestingly, the expression 2n plus 1 will, for any value of n from 0 to infinity, yield an odd number. Think about it. 2 times any n will be divisible by 2, and so by definition, it is even. Add 1 to any even number, and it will be odd. This means that every term we add to the sum will have an x raised to an odd power, meaning it's symmetric about the origin. Correspondingly, even though the sine function itself has no power of x, it's an odd function symmetric about the origin. It's a similar story for cosine of x, except here, x is raised to 2n, meaning every power of x that we add to the sum will be even. So the shapes that we see here are all symmetric about the y-axis. The final concept that we have to be very thorough with is the imaginary number, I. More specifically, powers of I. Let's take a look at the first few powers of I, starting with 0. By the 0th power rule, this is just 1. I to the first power is just I, and by definition, I squared is -1. I cubed is a little less intuitive, but if we just multiply I squared by I, we get -I. And so this process repeats as the power you raise I to increases, cycling through 1, I, -1, and -I, every 4 powers. Now it's time to put all these concepts together. As we know, we can use this summation to expand the function e to the x, but x can be any variable or function of x. So if we replace x with I times x, and now we're expanding e to the ix, which is equal to the infinite sum of I times x, the whole to the nth power over n factorial. Now, to understand why this sum can help us, let's expand the first 8 terms of the sum, starting at n equals 0 to n equals 7. We get something that looks like this. And we can go ahead and simplify the terms to get this. Notice how after you distribute the exponent to both I and x, the coefficient for x will just be the nth power of I. These coefficients that are powers of I give way to many of the patterns that we see in the expansion. It's noticeable that we have an alternation between positive and negative every 2 terms, meaning there's 2 positives, then 2 negatives, and so on. But I think the most important pattern is the alternation of real and imaginary terms that corresponds with even and odd powers of x, because it gives way to the idea that this series can be split up into real and imaginary parts. Let's go ahead and color all of the imaginary terms in red. By definition of infinite series, there will always be another term that we can add to the end of this. This means that for every red term, there will always be a white term to add to the end, and for every white term, there will always be a red term that we can add to the end. By these logical bases, we can conclude that the red and white terms each pertain to an infinite series of their own, and we can actually go ahead and split up this one expansion into the separate real and imaginary series that it consists of. Now, if we take a look at the red series, we notice that by definition of imaginary number, every term in this series is multiplied by I, so we can actually just go ahead and factor out I from the entire infinite series. Now what we're left with is 2 seemingly random series, but they can each be represented by these equivalent sigma notations, and if you recall from earlier, these are actually equivalent to sine and cosine of x. And just like that, we've demonstrated that e to the ix equals cosine x plus I sine x. If you made it this far, I want to thank you for watching, and I hope you learned something new. I programmed all the animations and shown this video using the Python library Manim, which was developed by my personal inspiration, Grant Sanderson, from the YouTube channel 3Blue1Brown. Also, if you're wondering about the background music, the piano you heard was just 7 minutes of improv I recorded for the video. If you're interested in other music I've done, or the source code for the animations, I do plan to put up a website with all my projects in the near future. I also plan to make a follow-up video on the topic, explaining practical uses for this equation, so stay tuned for that. Once again, I want to thank you for watching, and I'll see you next time.